So the next thing I want to talk about is separable differential equations. It's a type of differential equation that's pretty straightforward to do. Let's look at what it means to be separable. The differential equation can be written as dy dx equals g of x times f of y. So you can cross multiply. You can then have 1 over f of y dy g of x equals g of x dx. You can integrate and get the answer. Or you might see it like this, where the h of y, the y gutch is on the bottom. Again, cross multiply and integrate. So our first example, dy dx equals x over y. Cross multiplying, I get y dy equals x dx. Integrate both sides, pretty straightforward, just power rule. Y squared over 2 plus c1 equals x squared over 2 plus c2. Because when you integrate, you're supposed to add an arbitrary constant. But I've got an arbitrary constant on the left and an arbitrary constant on the right. I'll bring it over and have one arbitrary constant on the right, because who needs all these arbitrary constants? Well, let's just not do that at all. Let's just add the arbitrary constant to one side. So when I integrate this, I'll get y squared over 2 equals x squared over 2 plus plain old c. In fact, I'm going to take it a step further, but first I think I need more space. Yeah, that's better. I've got y squared over 2 equals x squared over 2 plus c. Let's multiply through by 2. So now I've got y squared equals x squared plus c. We're not done yet. We have to solve for y. We need to find what the original function was. So I take the square root of both sides. And remember, if you take the square root, it's plus or minus. I don't know which one it is. So that is our general solution. But what if we got an initial condition? What if we were told y of 0 is negative 2? Well, then we would do all the stuff we did before, but then we would go, okay, well, that means negative 2 has to equal negative the square root of 0 squared plus c. I know it's negative because I was told that y of 0 is negative 2. It has to spit out a negative number, so that's the version of the function I will take. Simplifying, I get c equals 4, and I'll plug that back into the original function. Let's look at another one that's a little bit more funky. Y prime equals x squared over y. Well, the first thing I'm going to do is change that y prime and use Leibniz notation. Leibniz is another guy who created calculus. This notation makes more sense when you are doing differential equations in separable. So I'll get the y's on the left and the x's on the right. So I get this. Integrating both sides, the natural log of the absolute value of y is equal to x cubed over 3 plus c. I know I can be somewhat loosey-goosey about doing the natural log of the absolute value. We need to be better about it during the differential equation section. So I've got the natural log of the absolute value of y is equal to x cubed over 3 plus c. Rewriting this exponentially, I get the absolute value of y is equal to e to the x cubed over 3 plus c. Now that exponent can be split up as e to the c plus e to the x cubed over 3. And when I lift the absolute value, I get plus or minus e to the c, e to the x cubed over 3. Now why would I do that? Well, c is an arbitrary constant, so e to the c is an arbitrary constant. Plus or minus e to the c is an arbitrary constant. The only thing I can't get here is a 0. But if I check the original equation here, y equals 0 is a perfectly good solution to this differential equation. So this coefficient out front can be any arbitrary number. So I'm going to rewrite it as a e to the x cubed over 3. Why, you ask, did I use an a? Because that's what everybody uses, and I'm just, a sheep. So these equations are straightforward. They're not bad. It harkens back to when you did implicit differentiation, because you've got all your x's and y's mixed up and you need to pull them apart and find the integral.